And we make one large and major distinction between the two major cell life forms on the planet in terms of cells. One are the prokaryotic cells, and these are the cells of bacteria. I'll show you an image of them shortly, which lack nuclei, and the eukaryotic cells, which possess nuclei and indeed have a highly complex cytoplasm and overall cellular architecture. We think that the prokaryotic life forms on this planet evolved first probably on the order of 3 billion years ago, maybe 3.5 billion years ago. And that about 1.5 billion years ago, cells evolved that contained nuclei. Again, I'll show them to you shortly. And these nucleated cells, the eukaryotes, then existed in single cell form for perhaps the next 700 or 800 million years, until multicellular aggregates of eukaryotic cells first assembled to become the ancestors of the multicellular plants and the multicellular animals that exist on the surface of the Earth today. To put that in perspective, our species has only been on the planet for about 150,000 years. So we've all been here for that period of time. And 150,000 sounds like a long time in one sense, but it's just a blink in the eye of the Lord, as one says, in terms of the history of life on this planet, and obviously the history of the universe, which is somewhere between 13 and 15 billion years old. You can begin to see that the appearance of humans represents a very small segment of the entire history of life on this planet. And here you can roughly see the way that life has developed during this period of time. From the fossil record, you see that many plants are actually go back a reasonable length of time, but not more than maybe 300 or 400 million years. Here are the metazoa, and this represents can you hear me? Yeah. Wow. 614 came in handy. Okay, so if we talk about another major division, we talk about protozoa and metazoa. The suffix zoa refers to animals, as in a zoo, and the protozoa represent single-cell organisms. The metazoa represent multicellular organisms. And we're going to be focusing largely on the biology of metazoan cells this semester. And we're going to be spending almost no time on plants. It's not that plants aren't important. It's just that we don't have time to cover everything. And indeed, the molecular biology that you learn this semester will ultimately enable you to understand much about the physiology of multicellular plants, which happen to be called metaphyta, a term you may never hear again in your entire life after today. That reminds me, by the way, that both Dr. Lander and I sometimes use big words, and people come up to me afterwards each semester, each year, and say, Professor Weinberg, why don't you talk simple? Why don't you talk the way we heard things in high school? And please understand that if I use big words sometimes, it's to broaden your vocabulary so you can learn big words. One of the things you should be, one of the big take-home lessons of this course should be that your vocabulary is expanded, not just your scientific vocabulary, but your general working English vocabulary. Perhaps the biggest goal of this course, by the way, is not that you learn the names of all the organelles and cells, but that you learn how to think in a scientific and rational way. Not just because of this course, but that this course helps you to do so. And as such, we don't place that much emphasis on memorization, but being able to think logically about scientific problems. Here we can begin to see the different kinds of metazoa, the animals. Here are the metaphyta, and here are the protozoa. Different words for all of these. And here we see our own phylum, the chordates. And again, keep in mind that this line right down here is about 550 to 600 million years ago, just to give you a time scale for what's been going on this planet. One point we'll return to repeatedly throughout the semester is that all life forms on this planet are related to one another. It's not as if life was invented multiple times on this planet and that there are multiple independent inventions. To the extent that life arose more than once on this planet, and it may have, the other alternative or competing life forms were soon wiped out by our ancestors, our single cellular ancestors 3 billion years ago. And therefore, everything that exists today on this planet represents the descendants of that successful group of cells that existed a very long time ago. Here we have all this family tree of the different metazoan forms that have been created by the floor at hand of evolution. And we're not going to study those phylogenies simply because we want to understand principles that explain all of them, not just how this or that particular organism is able to digest its food or is able to reproduce. Here's another thing we're not going to talk about. We're not going to talk about complicated life forms. We're not going to talk very much, in fact hardly at all, about ecology. This is just one such thing, the way that a parasite is able to tapeworm is able to infect people. This is, again, I'm showing you this not to say this is what we're going to talk about. We're not going to talk about that. There's a wealth of detail that's known about the way life exists in the biosphere that we're simply going to turn our backs on by focusing on some basic principles. We're also not going to talk about anatomy. Here in quick order are some of the anatomies you may have learned about in high school, and I'm giving them to you each with a 3-second showing to say we're not going to do all this. And rather, just to reinforce our focus, we're going to limit ourselves to a very finite part of the biosphere. And here's one way of depicting the biosphere. It's obviously an arbitrary way of doing so, but it's quite illustrative. Here we start from molecules, and in fact we will occasionally go down to submolecular atoms. And here's the next dimension of complexity, organelles, that is these specialized little organs within cells. We're going to focus on them as well. We're going to focus on cells. And when we start getting to tissues, we're going to start not talking so much about them. And we're not going to talk about organisms and organs or entire organisms or higher complex ecological communities. And the reason we're doing that is that for 40 years in this department, and increasingly in the rest of the world, there is the acceptance of the notion that if we understand what goes on down here in these first 3 steps, we can understand almost everything else in principle. Of course, in practice, we may not be able to apply those principles to how an organism works or to how the human brain works yet. Maybe we never will. But in general, if one begins to understand these principles down here, one can understand much about how organismic embryologic development occurs. One can understand a lot about a whole variety of disease processes. One can understand how one inherits disease susceptibilities. And one can understand why many organisms look the way they do, i.e. the process of developmental biology. And so keep in mind that if you came to hear about all of these things, we're going to let you down. That's not what this is going to be about. This also dictates the dimensions of the universe that we're going to talk about, because we're going to limit ourselves to the very, very small and not to the macroscopic. On some occasions, we'll limit ourselves to items that are so small you can't see them in the light microscope. On other occasions, we may widen our gaze to look at things that are as large as a millimeter. But basically, we're staying very, very small. Again, because we view, correctly or not, the fact that the big processes can be understood by delving into the molecular details of what happens invisibly and cannot not be seen by most ways of visualizing things, including the light and often even the electron microscope.